In our previous video, we had introduced how basic Perceptron model works. Today, we are going to create a simple Perceptron model that can be used to automate the operation of a basic agriculture sprinkler system. The idea is to create a basic decision-making based on Perceptron model that turns the sprinkler on or off based on two inputs, temperature and soil moisture. This automatic sprinkler controller can be viewed as a very simple neural perceptron whose job is to decide, based on readings from two sensors, whether to turn on the water. The two diagrams encapsulates a simple yet powerful decision-making architecture. On the top is the flow chart of the computation, and the bottom diagram shows the corresponding perceptron network. The main component of the perceptron-driven controller are the 1. Sense moisture and light. 2. Weight each input according to its importance. 3. Sum the results into a single activation score. 4. Threshold that score to yield a binary decision. 5. Actuate the sprinkler hardware on negative activation. This Perceptron-inspired controller is easy to understand, quick to compute, and most importantly straightforward to tune so that the garden receives just the right amount of water. At the front line of this controller are two physical sensors. Soil moisture sensor. This device measures how much water is present in the ground. Typically, it outputs an electrical signal, voltage, or resistance that rises as moisture increases. Sunlight sensor. This device measures ambient light intensity. Again, it produces an electrical signal which increases with the amount of sunlight. Taken together, these two readings represent the key environmental factors that determine whether irrigation is needed. If the soil is dry and the sun is strong, the plants are likely losing water faster than they can absorb it, so the sprinklers should run. Not all inputs should count the same. A brief midday shower might leave the soil damp even under bright sun, for instance, whereas overcast days with very dry soil still demand irrigation. To capture these nuances, each sensor reading is multiplied by a parameter called a weight. W1 scales the soil moisture reading. W2 scales the sunlight reading. Thus, after weighting, the two signals become W1 times soil moisture reading and W2 times sunlight reading. By adjusting W1 and W2, you decide how heavily to trust or emphasize each sensor. Once scaled, the two signals enter the summing junction, where they are added together to produce a single scalar value called the activation. Activation equals W1 times soil moisture reading plus W2 times sunlight reading. This activation represents the system's overall assessment of irrigation need. A highly negative activation, for instance, if soil moisture is very low and sunlight is high, signals strong evidence that water is required. A positive activation suggests the soil is sufficiently moist relative to sunlight. Raw activations can vary continuously, but the sprinkler system must make a binary choice, on or off. To convert the continuous activation into a discrete decision signal, we apply a step function, sometimes called a sine function. After this mapping, an output of -1 indicates the activation fell below 0, i.e. soil dryness outweighs moisture, so turn sprinklers on. An output of +1 indicates no need for water, so keep sprinklers off. Training a perceptron for your sprinkler system involves 1. Defining sunlight and soil moisture as inputs and sprinkler activation as the binary output. 2. Gathering representative training data, covering various scenarios. 3. Initializing the perceptron with random weights and bias. 4. Choosing a step activation function. 5. Iteratively feeding training data, calculating the error, and updating the weights and bias using a learning rule. 6. Evaluating the trained perceptron on unseen data.